Yes. Okay. Okay. So as I was saying that thermodynamics, so many systems we have to manage all together to take a class, and it's so much confusion. Anyway, chalo. So what I was saying is thermodynamics. I think you may have already heard this, bifurcation or definition that thermodynamics is made up of two words, thermo and dynamics. Thermo is basically what? What do you mean by thermo or thermal? Can anyone tell me quickly? You have to be very responsive. Okay. Yes, very nice. Thermo means heat. What is dynamics means? Dynamics means motion. Yes, motion. If something is in motion, you can say it's dynamic. Okay, so basically when heat is causing the motion of what? Motion of atoms or molecules. So we can, if we are studying the motion that is caused by heat, that study we do it in thermodynamics. So it's simple word. If heat or energy is causing a motion of what? Atoms or molecules. So if motion is happening, then what will happen? Its pressure will change. Atoms, okay, its pressure will change, its velocity will change, its temperature will change, okay, and other properties may also, its energy will change, internal energy will change, entropy will change, everything like well, properties will change. And we study that how these properties are changing, okay, due to heat transfer or energy transfer. So that study we say that it is thermodynamics. Okay, so what is the scope to study? Okay, to study where motion of the atoms and molecules of a substance is caused by heat or energy. So here basically it is a branch of science which deals with energy conversion and its effects on physical properties. What is this? This is physical properties. What is the pressure? What is the temperature? These are all physical properties. Okay, so here we deal with energy conversion, how the energy is converting, and what is the effects it is causing on the properties of the substances. This is what we do study in thermodynamics. Okay, now what is the ultimate aim? What do you want from thermodynamics? Okay, ठीक है, whatever is happening with pressure is changing, volume is changing, velocity is changing, temperature is changing, whatever is happening, it's fine. But why do we need to understand it? Why we have to study the whole subject to understand how these things are happening? So the whole objective, the ultimate aim is to basically understand when this conversion is happening, then how we can make an effective conversion, basically how to effectively convert one form of energy to another form, so that we can, so whenever one form of energy is converted from to another form, okay, we can utilize this energy in some form. We can convert it into work, we can convert it into electrical energy, okay, we can convert it into velocity or potential energy. So basically the aim is what, how to convert this in an effective way. When we are converting one form to another, how to do it in a very effective way, okay, with minimum entropy, with minimum losses, in a very reversible way. So how to reduce irreversibility, that is the ultimate aim of the thermodynamics. All these things we are going to discuss, do not worry. Okay, now there are basic definitions. What are the basic definitions? So first of all is a system. Now what is a system? Basically anything around you over which we are going to, do a study, or we are going to focus on something, that is our system. For example, you have your, I mean, like people say system, but still we have a very vague idea about what a system is. So I'll tell you one thing. For example, you have a power plant, so you have a heat exchanger here, you have a compressor here, let's say, or a turbine, let's say, here. You have another heat exchanger here. Okay, then a pump here, let's say. Okay, pump, turbine, heat exchanger. So at a particular time, we are only going to focus on one system. For example, we are only focusing on this heat exchanger. What is happening in this? If hot fluid is entering, cold fluid is also entering, hot fluid is coming out, whatever is happening, but we are focusing on this. So our focus is on this heat exchanger, and then this is our system. This is our system. We can also take more than one system. For example, we can take this system. Now we have two systems here. So whatever is entering here, whatever is coming out, but we are going to treat it as a black box, and this is our system. We can take three systems as well. We can take all of them. We can take them as a whole system. Although then it will be a cycle, but still we can treat it as a system. Okay, so system is something that we are focusing on, which we are going to study how the properties inside the system is changing, is basically our system, our focus. Whatever is our focus, that is our system. And it's very important to determine what is your system, because a lot many problems you will face, that there are so many unknowns and you are not able to solve them. Why? Because you did not decide your system properly. Okay, so you have to see what is the, if you want to solve a problem, you have to see what system to choose. Okay, that we are going to see when we solve a few questions, or we can see that. One second. Okay, so this will be our system, and anything outside the system. Now let us say this is my heat exchanger, and I have chosen it as my system. Now anything external to this is surrounding, and this system and surrounding is separated by something that is called as boundary. Now this boundary can be real or imaginary. It can be real or imaginary. Okay, here we can see a real boundary, but it could be, for example, there is a very long pipe, very long pipe. So you cannot pursue a study on this whole pipe. So what will you do? You will imagine a imaginary boundary like this, and then you will see how the fluid is entering, at what pressure, at what velocity, and at what entering, at what pressure it is exiting, at what velocity it is exiting, and you perform your analysis. So in this particular time, we have imaginary boundary. Okay, we have imaginary boundary. So boundary can be real or imaginary, and everything, system, surrounding, boundary, everything constitute is called as universe. Is it clear? Yes or no? Quickly tell me. Okay, very nice. So very important things about boundary. So it is a surface through which system and surrounding interact. So basically boundary is the separation between system and surrounding, and this is how. So if, yes, boundary we are anyway discussing. You see, this here we have focus on boundary only. Okay, so basically, if this is my system and this is my surrounding, so if system and up, now how are they separated? They are separated by a boundary. Now, if system and surrounding have to interact with each other, then how are they going to interact? They have to interact through the boundary. So for example, heat transfer, we are going to see heat transfer is happening from the system to the surrounding. That means both system and surrounding are involved. So they heat transfer has to cross the boundary. If heat transfer is happening inside the system itself, it is not interacting with the surrounding. Okay, so in order for the system and surrounding to interact, that thing must cross the boundary. It should go through the boundary. If something is happening inside in the surrounding, heat transfer is happening outside from one body to another, it does not matter. You cannot say it. We are not going to focus on this. We are not going to focus on this. We are only going to focus what heat transfer is crossing the boundary. That's all. Okay. Just 1 second. Okay. So this much is clear, Amit. First of all, then we will discuss more about boundary. Yes? No, Amit? Anyway, so as I told you earlier, boundary can be real or imaginary. I have showed you example as well. Okay, this is a real boundary. This is a real boundary, and this is the imaginary boundary. Okay. Now, next thing is real boundary is shown by continuous line, and imaginary boundary is shown by share first slide. What slide? This one. This one. You will get all the slides anyway. Don't worry about it. I mean, are you trying to write it with me? Don't try to write anything, okay? Just try to understand what I am saying, and you will get the PPTs. What I am writing also you will get with the PPT. Whatever is written on the PPT, you will get that. Whatever I am writing also you will get that. Okay. So focus on what I am saying. Not because if you try to write everything, then I cannot cover much. Okay. So don't try to write. If I am saying something and you think it is important or you will forget it, maybe just try to write that. Okay. So as I showed you, it can be real or imaginary. Now real boundary is shown by continuous line. You see, this is a continuous line, and imaginary boundary is shown by dotted line. What else? Now boundary can be fixed or movable. Boundary can be fixed or movable. What do you mean by this? For example, you have a pressure vessel. Pressure pressure vessel. Okay, like this. Now it has a fixed boundary. It is not going to move. Okay, like a solid cylinder or something, it's fixed boundary. So this is called as fixed. It is not going to change. But what is movable boundary? For example, you have this. You have a reciprocating cylinder and you have valves here. So when fluid is going to come inside this, and let me show the boundary also. For example, right now this is the boundary. Okay, now when fluid will flow inside, this piston is going to move in this direction. So the boundary is going to change, boundary is going to expand like this. And when fluid is going to come out, then piston will move in this direction. So boundary may reduce. Okay, so this is called as flexible boundary or movable boundary. Movable or flexible. Okay, is it clear? Yes, what do you, Shivam, what fixed and movable you want me to repeat? It's very simple only. You see, look, if you take a piston cylinder and there are no walls in it, there are no valves, then what is the boundary? Boundary is this. This boundary is not going to change. Okay, it is fixed. But if you have a piston cylinder with a valve, valve means fluid can come out, fluid can go in, and this is your piston. And right now this is your boundary. This time this is your boundary. But let's say fluid is coming in, so this piston is going to move ahead forward. So you see, this line is going to change, this one is going to change, so boundary is increased. If fluid is coming out, then piston is going to move in opposite direction, so this boundary is going to reduce. So this, you see, green line is moving in this direction. Earlier it was moving in forward direction. So now boundary is changing. So this is called as flexible boundary. Okay, chalo, let's move ahead. Now the systems can be classified as closed, open, and isolated. But in what terms? How are we classifying? Okay, if we are classifying something, it should be on some basis. What is the basis? As I told you that this system can interact with surrounding. But how is it interacting? It can only interact in two ways. First, and I told you one thing already. If I am saying these two things are interacting, that means that thing should cross the boundary. So mean if any mass is entering or any mass is leaving, mass out or in. So where it is coming from? It is coming from surrounding. It is coming from surrounding and entering into the system. It is crossing this boundary, you see. It is crossing this boundary. Similarly, it is coming out from system and going to surrounding. So this is called as mass interaction. The another type of interaction is energy interaction. You see energy when energy comes in from the surrounding to the system, and when energy goes out from the system to the surrounding. So again it is crossing the boundary, you see. It is crossing the boundary. That means a system and a surrounding can interact only by two ways, mass and energy. So either mass transfer and energy transfer. And why do we say transfer? Because it is moving from one place to another. That is why we say transfer. We do not say just mass, because mass in itself is nothing. Okay, it is, if the system and surrounding has to interact, if some mass is sitting inside this system, then it is internal mass, it is not interacting with the surrounding. For the interaction to happen, it should transfer from the system to the surrounding. That is why we say mass transfer, energy transfer. Now based upon this interaction, our system is classified on closed, open, and isolated system. Okay, now what is closed system? Closed system is basically when you see, if this is your system and this system will not allow, it will not allow any mass transfer. Mass, no, how can I say, mass transfer is equals to zero. No mass transfer can happen. This boundary is not going to allow any mass transfer. What can you say? Like for example, you have a piston cylinder like this. Okay, now it has no valves. Let us say it has no valves. There, if there are, okay, sorry, we have a piston cylinder arrangement and it has no valves. Some mass is there already. Okay, here we have some mass inside the system. Now let us heat this. Okay, let us give some heat, or provide some heat. Now, why, how are you heating it? You are putting a fire or something, whatever it is happening. Now because of this heat, you are heating on other side. Okay, this is surrounding part. You have lit a fire, and because of this fire, heat will get transferred from the system to the surrounding. But there are no valves here. So because there are no valves, you cannot transfer mass here. Because of this heat, this mass will heat up, its volume is going to increase, and this piston is going to move forward. Or if you are taking heat out of the system, for example, you have installed a heat exchanger here both sides, and this heat exchangers are taking out heat from here. Okay, so volume will decrease and piston will go in. So basically what I am trying to tell you is, it is a system that is not allowing any mass transfer. What it is allowing? It is allowing only energy transfer. Two type of transfer can happen: mass transfer and energy transfer. But closed system, can only allow energy transfer. No mass transfer is allowed. No mass transfer. That means if no mass is entering or leaving, that means it is a fixed mass system. It is a, because whatever system has mass, it is fixed. No mass is entering, no mass is leaving. Okay, this is a fixed mass system. And also it is called as no flow, non-flow system. Non-flow system. Okay. So these are the things that is same thing is written here. Mass of the system remains same, but the volume, you see, volume is changing because energy is, because heat is non-flow. Flow basically, if mass is flowing, then you can say flow process. It is, don't go about process here. Let's say system as of now. When we understand process, then we will go to process. Let's say system. Okay, it is a non-flow system. And non-flow, we are saying in terms of mass, because mass is not flowing, that's why no non-flow. If mass will be flowing, it will be a flow system. Okay, so same thing I have told you. Okay, the important point here to note is, the first point is there is no mass transfer, second point is only energy transfer, and the third point is it is called as fixed mass or non-flow system. Okay, now adiabatic boundary is basically not allowing any heat transfer. Adiabatic is what? No heat transfer. So you see, energy also, we are going to see later on, energy is also get transferred in terms of heat and work. So we are going to see later on. Now, if this boundary is adiabatic, then only work transfer will happen, no heat transfer. And rigid boundary matlab no work transfer as well. Okay, although it's not very frequently used, rigid is not very frequently used. Adiabatic is very frequently used. Adiabatic matlab no heat transfer. Adiabatic means no heat transfer. You remember this. Bound, basically we have insulated this boundary, we have provided a very strong insulation here, so now it is not allowing any heat transfer also, it is not letting the heat to go inside. Okay, now next is open system. What is open system? Simple. Open system means whatever restriction we had, now we have, let's say, piston cylinder arrangement, and we have valves here. Okay, so adiabatic is closed or isolated. No, I am talking about boundary. Boundary is adiabatic. Okay, isolated means no. We will talk about isolated. Wait, Abhishek, though. Wait 2 minutes. We'll talk about isolated. Okay, adiabatic simply means no heat transfer, nothing else. Okay, it could be adiabatic flow system can also be there. Okay, so adiabatic, you just remember, you don't confuse adiabatic with closed or isolated. Adiabatic simply means no heat transfer. Everything else can happen. Work transfer can happen, mass transfer can happen, everything can happen. Okay. Now, if we have this kind of system and we have put a fire also here, you see, I have put a fire also here at the center. Some fire also I have put. Now, what is happening? And this is my system. It has some mass of system as well. Okay, now what is happening, some mass is coming in, some mass is coming in, and some mass could be going out as well. Now based upon how much mass is coming in, how much mass is going out, this mass of system is going to increase or decrease. For example, 10 kg per second is coming in, mass in is 10 kg, mass out is 20 kg per second. That means going out is more. So this mass of system is going to reduce. Okay, it's simple. The case of your bucket, like your drum, water drum or bucket. For example, in that drum, you have already 50 liters of water. Let me say it in terms of kg. Otherwise, again, you will get confused. 50 kg of water I am saying. I know it is not correct, but because we say water in terms of liters, but anyway, 50 kg of something. Okay. Now you see 20, 10 kg is coming, 20 is going out. So what will happen? This 50 is going to reduce because more is going out. So mass of system is going to reduce. Similarly, vice versa, if more is coming in, less is going out, then mass of system is going to increase. So it is allowing the mass transfer. First of all, it is allowing the mass interaction. Also, heat will go in. So energy interaction is also happening, energy as well as mass interaction. And because mass interaction is happening, it is called as flow system. Okay. And here we basically focus on definite volume or control surface. And for and actually most of your power plant systems, for example, heat exchangers, compressors, another heat exchanger, turbine, they are all what flow system, because you see mass is going out from this heat exchanger and entering into the compressor. Then it is coming out of compressor, it is going into turbine. So mass is continuously entering, continuously going out. So they are all open system. Most of your power plant equipments are open system because mass flow rate happens there. Okay. Boiler, condenser, turbine, and arrangement, piston cylinder arrangement with valves. Okay. Next is, so open system, as I said, steady flow, and there are two types of open systems: steady flow, unsteady flow. What do you mean by steady flow? Steady flow means, it simply means mass of the system with respect to time is equal to zero. There is no mass of the system is not changing. Similarly, let me say delta m. And similarly, energy of the system is not changing with respect to time. So what does it mean? For example, mass of system is there and mass is coming in and mass is going out. Now in steady flow system, this mass in will be equal to mass out. It is a compulsory condition for steady flow. And if entire engine, yes, I mean reciprocating engine, if you say, it is a open system, because you see air comes in, fuel comes in, all that thing mixture comes in, they're all open systems. Okay. So steady flow systems are, it is a necessary condition. So mass in is equals to mass out. And if mass in is equals to mass out, that means this mass inside the system with respect to time, it is not going to change. So it will be equal to zero. It will be equal to zero. Okay. So there is no mass change of the system. Mass inside the system is constant simply. What about unsteady flow? Unsteady flow means mass of system is there, mass in and mass out. Now it's unsteady means mass dot in is not equals to mass flow rate out. If they are not equal, what will happen? For example, more mass is coming in, less. For example, m dot in is less than m dot out. So it is less is entering, more is going out. So what will happen? Mass of system will decrease. Okay. If mass flow rate in, if coming in is more, than what will happen? Mass of system will increase. That means your mass of system is not equal to zero with respect to time. It is changing, mass is changing with time. And here mass is constant with time. Okay. This is your steady, this is your unsteady. Tell me very quickly, is it clear? Okay, very nice. Also, I would ask you to can you tell me, have you studied thermodynamics before? Very quickly, like, are you studying everything the first time, or you have already done it? Okay, I think most of people have already done it. Anyone who is studying it the first time, who has not, I mean, I know you would have studied in college, but I know how you study in college. So okay, Ravi Teja is first time, already done it. Amit, very nice. Yeah, I know how you do in college, so I would not. I mean, I would not expect much if you are saying about college, but for GATE or for any other exam, if you have done it, then I would be very happy. Suryan's is first time. Okay. Anyway, so it's my really humble request to all the people who are doing it the first time. No, sir, in college only. Okay, Sonali, it's okay. So college, who are people who have done it in college, I really don't. Yes, I studied for GATE. Okay. So I really don't expect much because I know how you study in college. You just study like 2 3 days and just okay, ठीक है, let me pass and all. I have to study six more subjects. But basically, if you are studying for GATE, you need to be focused. And I would request everyone to at least give it a read. Okay, take any notes, whatever it, because you see it is a very brief sessions. Okay, so I will try to cover everything, but I cannot go slow. Okay, so if you ask me to repeat one topic again and again, it will be really difficult content wise to cover those content. Okay, so I have to stress that time. Okay, so basically I will be going to cover everything, but I would also expect you to study, have some little idea about what we are going to study, and little idea about thermodynamics, so that we can quickly move over other topics. Also, what actually happens is when you ask small doubts, no, like when you ask me to, sir, repeat this again, repeat that again, and if it is a complicated topic like entropy or something, or something like really complicated, it's really fine, you can ask me 3 times to repeat. But if it is a simple topic and you are asking me to repeat, so what you are doing is you are wasting time that we can utilize in complex topics to study, to give it more time. So it's basically your loss only because I already know those topics. So I would not be able to spend more time in those topics. Okay, so please pay extra attention. Please try to figure out questions that you want to, like just try to be focused on. If you are focused on what I am saying, I think most of the doubt will already be cleared. Okay, but anyway, you are always open to ask, sir, please repeat. I just expect you to be more focused and try to read more. Okay, chalo, let's move ahead. Let's move further. Isolated is simply means, look, these things are never asked in exam. Okay, it's like very rare they ask. They are very small concepts. So let's move ahead very quickly. So closed system was no mass transfer, only energy transfer. Open system was both mass transfer and energy transfer. What about isolated system? No mass transfer, no energy transfer, simply. It's PK Nag is there very okay for aerospace. You have to be follow something more specific. I need to check. Usually, I tell for mechanical people PK Nag. Okay, but for because PK Nag has too much content. If you start studying PK Nag, then you will waste a lot of time. Although it's a very good book. Okay, Sangel is good. I mean, but Sangel is good for concept point of view. Like if you want to actually understand thermodynamics, so like theory wise, if you for I would suggest Sangel to someone. For example, you are stuck at a topic, you are stuck at you want to know the physical significance of something, then I would say you go and study that particular topic from that Sanjal. Shapiro is good, yeah. Shapiro is actually good book. For aerospace, I think that is recommended, yes. Okay, chalo. So basically, for example, you have a thermo flask. You know these thermal bottles that you buy from, what is the famous brand? There is a very famous brand. No, I don't remember. Okay, so what? Milton, yes, very nice. Milton, yes. So you see these bottles. and you fill up water. Okay, so once you have filled up the water and you close it, once you have, okay, you have opened it and filled it, okay, that's fine. But once you have filled it, now water is there. So now no water is going out of the system, and also no heat is, you see, normally it will get, for example, you have filled it with hot water. So now it will take around 10 hours to go from 50 degrees Celsius to the surrounding temperature of 25 degrees Celsius. Why 20, why it is taking 10 hours or 8 hours? Why? Because you see, energy transfer is happening, but it is significantly less. It is very, 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 very less. So you can say basically in rough terms that no energy transfer is happening. Okay, so this can be considered as isolated system. Or example, your universe, you see, this is your universe, and that is why we say energy of the universe is conserved, because you see, nothing goes out of system, is also here, surrounding is also here, everything is inside the system, inside the universe. So nothing goes out, no mass goes out of system, no energy goes out of system, and that is why I say universe is an isolated system. Okay, so basically this is a closed system with no energy interaction. So closed system, what is closed system? No mass transfer. If there is also no energy transfer in closed system, it will be isolated system. Okay, chalo. Now very important terminology in thermodynamics, very important. Everything we are going to discuss, these terms will come again and again and again. Okay, let's start with this. Just 1 second, give me 1 second. Okay, so there are these five things that we are going to discuss. This terminology will come so many times. What is the property? How the property is changing? What is the state of system? Thermodynamic path, process, and cycle. So what are these? What are these? Let us discuss them one by one. First, let us go to property. What is the property? Property is, you see, if I want to describe you, how would I describe you? For example, like, what is your height, what is your weight, what is your like, what is your qualification. So basically it's the characteristics. It is the how, if I want to define something, yes, characteristics. Okay, so if I want to define something, I will define it by characteristic of that thing. And if I have a system, I have already told you what is my system. For example, I have a heat exchanger. Okay, so, or a compressor or a turbine. So what is the pressure in this system? What is the temperature? What is the volume? So these are characteristics. Now it can be identified, observed characteristic that depends upon the state of system. Okay, so based upon what you are giving, how much energy you are giving, how much mass is entering, so these characteristics are going to depend on that. And it can be measurable, for example, pressure, volume, and temperature, and unmeasurable, like enthalpy and internal energy. Now, so many times you will see that when people teach thermodynamics, they will always say, what is the property? It is the measurable characteristic of the measurable of the system of the system, measurable characteristic of the system. It's not necessary; it could be measurable. You cannot measure enthalpy. You see, you cannot install a system here, or like a device, and you can measure enthalpy. It's not possible. You cannot measure internal energy of the system. There is no device that can measure internal energy. Okay, but they are properties. Okay, so it can be measurable, it can be non-measurable. Now then, how do you measure, how do you define these? Basically you define these unmeasurable properties in terms of measurable. For example, enthalpy is defined as U plus PV. And what is U? U is equals to MC T. Now temperature is measurable. So U is equals to mct. You can measure temperature. That's how you can define this unmeasurable quantity. Now similarly you can measure this by, you can measure pressure, right? You can measure volume, pressure gauges you have, okay, and temperature or thermometer you have. So you define these unmeasurable quantities in terms of measurable quantities so that you want to give it a value, but they are all properties. So property can be measurable, can be unmeasurable. Now there are two types of properties, extensive and intensive. Okay, now what is an extensive property? Extensive property is a property which depends upon the mass or extent of a system. Mass or extent of a system. Okay, now what do you mean by mass or extent? Extent means size. Okay, so you see, if I increase the mass of the system, then if the property is changing, then it is a extensive property. If there is no effect on the property, then it is intensive property. Okay, it is extensive is basically it is dependent on mass or size. For example, mass, volume, internal energy. You see, internal energy, how do you define internal energy? M C T. So it is dependent on mass. How do you define enthalpy? Enthalpy is defined as U plus PV. What is U? MCT. What is P? We will see ideal gas equation, PV is equals to MRT. So MRT. So basically it is also dependent on mass. CT plus MR. It is also dependent on mass. Similarly, entropy is also dependent on mass. Okay. So these are all properties, they are dependent on mass. What about intensive properties? So intensive are basically they are not dependent on the mass. They are independent of mass or extent of the system. And also two extensive properties is a intensive property. So for example, you see, what is the extensive property? You see, mass is an extensive property. Okay. What is volume? Volume is extensive or intensive property? Extensive. So if I divide this mass by volume, what do I have? I have density, and density is basically a intensive property. Yes. So numerator is extensive, denominator is extensive. So ratio of two extensive properties is intensive. Also you can take it in a way that if you have, you see, what is capital H? Capital H is M C, or let me tell this in terms of internal energy. U, capital U by mass is equals to mct by mass, and mass get cancelled, ct. So now this is independent of mass, and this is called as small u, or specific internal energy. So this is also, you see, this is extensive property, this is also extensive property. Ratio of two extensive properties is intensive property. Got it? So you can either say this, or you can also say specific extensive property is intensive property. So this is the example of specific. So this is specific internal energy, and this is intensive property. So you see, when I, this is extensive property, right? This is extensive property. Now, so I can say internal energy. Now, if I say specific extensive, yani ki if I say specific internal energy, so what is this? Small u is equals to capital U by M, and this is intensive property. Okay, specific means per unit mass. Yes, that is a general definition. If you divide something by mass, you call it specific. For example, capital H, you divided mass, specific enthalpy. Entropy divided by mass, specific entropy. Okay. So specific means per unit mass. Yes, that is true. Got it? There is just one exception to it. That is, if you divide Q by M, it is not called a specific heat. Specific heat is Cp. Okay. So Q divided by M is basically you say Q dash or something. Okay. One exception to this rule. Otherwise, specific means per unit mass. Clear? Yes or no? Quickly tell me. Okay. So you can see this. For example, you can take a system. You have this one system, and here you see pressure is P, temperature is T, volume is V. Now let me take one more system here. Here also pressure is same, temperature is same, volume is same. For example, if this is 10, this is 20, and this is 5, so this is also 10, this is 20, and this is 5. Okay. Units I am not saying. For example, this is in kilopascal, this is in Kelvin, this is in meter cube, whatever units you want to assume. Okay. Now, this is volume, okay? Not velocity, volume. Now, let me remove this barrier from here. So if I remove this barrier, it is a removable barrier. So let me remove this barrier. So if I remove this barrier, tell me what is the pressure of this system now? Quickly tell me. Is it P? It is 2P. It is P by 2. Yes, it is 10. That means P. What is the temperature? Temperature will be, yes, 20. What is volume? Just 1 second. Someone was asking something. Yeah, volume is 10. So basically, volume has doubled 2V. Okay. Someone was asking something. 1 second. Who was asking? Bhaveshri. Okay, just wait. I'll explain. I'll explain. Okay. So that means you see mass is increased here. Mass is become doubled. Here, if it is mass and here it is M, now it is become 2M. Okay. So because of this mass or the size, pressure has no effect. Pressure has no effect on it. Temperature also remains same, but the volume has changed. So that is why we say these are intensive properties, these are extensive properties. Now, Bhaveshri was asking something, how specific extensive property is intensive property. It's simple. You see, H is equals to M, not then I have to write the whole formula. Let me write. Okay, let me write H only. HCPT. Okay, this is also how I can write this. H. Now you see, this is this depends on M. Now if I divide this thing by M, this is also I divide by M. So what is the final expression? You will have Cp into T. Now is there any mass term in it? For example, your mass is 10 kg. Your mass is 10 kg. And you have to calculate H. So if you want to calculate H, for example, Cp is 4.18, and let me write 4 only. Okay, let me write 4 only. Cp is 4 and temperature is 100. Okay, and I want to calculate H when mass is equals to 10 kg. So I let me calculate small h. Small h is Cp into T. That means 4 into 100 is equals to 400. Now let me increase mass by 20 kg. So let me calculate small h again. Cp into T, 4 into 100 is equals to 400. Is my h changing? Small h. It's not changing. That's, I mean, once you divide it by mass, that means it is become per unit mass. Here, everywhere, my mass is equals to 1 kg, simple. My mass is equals to 1 kg. Is it clear, Bhavya? Bhavya Shri was asking, I think. But you see, capital H will change. So capital H here will be 10 into 4 into 100. Then again it will be 20 into 4 into 100. Okay, it is going to change. What is it no for? Did you not understand or not change? Tell me, okay, you tell me yes or no if you understood the concept. Yes or no? Okay, understood, understood. Okay. Bhavashri, you want me to explain again? What I mean, I have explained it using two methods, and I really cannot make it more simpler. But ठीक है, just for your sake, I'll explain it one more time. Look, extensive property in the same volume container, if we add more gas, then density will not density increase like in LPG cylinder, same volume. But you have to increase the volume as well, no? You see, density is equals to mass per unit volume. So if you are changing mass, so it is going to compensate, volume is going to compensate for it. Okay. For example, if this is the container and first mass is basically, let's say 10 and volume is what, 5. Okay. So if you increase the mass, what will happen? Volume will decrease. Volume of mass changes as we use it. I mean, basically here volume will remain fixed, but basically for density, you if the mass is changing, then volume will automatically adjust itself so that density will not change. Okay, density is what? Density mass per unit volume. Okay, so number of atoms per unit volume. Per unit volume, volume is one. It is 1 meter cube. How much mass can you accumulate in 1 meter cube is density. Simple. Volume you will take 1 meter cube. Okay. Now coming to Bhagyashri. How can I explain you one more time? Okay, let's see. Uh, okay, I'm running out of ways. ठीक है. Look, H is equals to M CP T. Now mass is equals to 10 kg and mass is equals to 20 kg. Okay. So if I calculate mass, it will be 10, and let me take Cp is equals to 4 joule per kg Kelvin, and temperature is equals to 400 or 100, let's say. So if I want to calculate capital H, now you see it is dependent on mass. Okay. So I can say 10 into 4 into 100. So whatever it will come, it does not matter. Then H1, H2, 20 into 4 into 100. Okay. Now what is small h? It is specific enthalpy. That means capital H divided by M. So M Cp T by M. So M and M will get cancelled. So it will be 1 into Cp into T. Now everywhere mass will remain 1 kg only. Mass is not changing. Okay. Specific enthalpy is calculated always by taking as mass is equals to 1. You take whatever mass you want in your system, it does not matter. Specific enthalpy will remain same if you are not changing temperature. Okay, so now if you want to calculate H1 is equals to 1 into 4 into 100, and H2 is equals to 1 into 4 into 100. So it will remain same only. Okay. So for all the specific quantities, you take per unit mass. Per unit mass means simple. It is 1 kg mass. It does not matter. You always take 1 kg. Okay. Is it clear? We have to quickly move on. Bhavishri, quickly tell me, is it clear? If it is not clear, then once you saw, like you will start using this, it will come into your habit. Okay. We are actually running out of time. 21:48 is already happened. Only 1 hour is left. Okay. And I think we have not even covered half of it. Chalo. Thermodynamic state. State means what? When, so I have told you about properties, pressure, volume, temperature, and all. Once you fixed, I fixed, when you fix the values of the property. Yes, yes, with temperature and pressure will increase. Yes, of course it will. You see, PV is equals to nRT, MRT. P is equals to density RT. So if pressure is density is equals to P upon RT. Okay, if pressure is increasing, density is going to increase. If temperature is increasing, density is going to decrease. Okay, we will discuss. They don't worry about it. Don't, like, let's focus on where we are. Okay, state. So basically, if you fix the value of properties, for example, I have fixed pressure is equals to 10 kilopascal and volume is equals to 5 meter cube. So what will I do? Let me fix 10 kilopascal here and I have fixed 5 meter cube here. And if I come to a point, this is my state of system. So in order to define the state of system, you should have definite values of the properties. When the properties of system have definite values at a particular time, the system is said to be exist in a definitive state. So basically, you see, if you are giving heat, its temperature is, let's say, 30 degrees Celsius. If you are continuously giving heat, its temperature is going to change 31, 32, 33. So you cannot fix it. Okay. So basically, you have at a particular time only, let's say you have defined 30 degrees Celsius is fixed and pressure is 1 kilopascal is fixed. This is your one condition. So this is your one state of system. Then, or let me explain it in this way. You have a system whose initial pressure is 1 kilopascal and volume is 5 meter cube. Temperature is equals to 100 degrees Celsius. So this is my first stage, state 1. Now what I do? So this is my fixed state. Now what I do? I will start giving some heat. I will start giving some heat. So what will happen? Pressure is going to increase, temperature is going to increase, volume is also going to change depending upon how pressure and temperature is increasing, how boundary is changing. So basically what I'm trying to tell you, these properties are going to change. Okay, now when these properties are going to change, what you can do? You can mark them. Okay, so first of all, you have marked here 10 kilopascal and 5 meter cube you have marked. Now you are giving heat. So maybe pressure is decreasing. Why? Because your boundary, the piston is expanding, the cylinder, the volume is expanding. So you see your volume has increased and pressure has decreased. Similarly, pressure has further decreased, volume has further increased. So you have to relate with this. You are giving heat, pressure is changing, volume is changing, and temperature is also changing. And until and unless you keep giving heat, this is going to change. It is going to further change. So you see, it is taking some intermediate pressure and temperatures to determine the path. So the series or succession of state passed during a change of, this is one state, you see, and now it is changing slowly, slowly, slowly. So whatever series, whatever points it is taking, it is called as path. It is called as path. Now eventually what will happen, you stop giving heat. Eventually you stop giving heat. So once you stop giving heat, then you will have a final pressure. Let us say, uh, now my volume was increasing. Let us say it has 15 meter cube, so pressure is decreased, let's say 0.5 kilopascal. Okay, and temperature is also, let's say, 50 degrees Celsius. I will tell you, Abhishek, don't worry about that. Okay, now, so now you have stopped giving heat, so finally we have reached at this point. So again, this is my fixed state. Between these two states, your properties are continuously changing. So you cannot fix the state. Now this is my state 2. Okay. So from coming from state 1 to state 2, whatever path you have taken, whatever points you have taken is called as path, and the complete thing from state 1 to state 2 is called as process. Okay. Now, Abhishek is asking how many properties should require to fix the state. It depends upon what kind of system you are working in. Okay, there is a law, Gibbs phase rule, that you use. Gibbs phase rule: P plus F is equals to C plus 2. Okay, so if phase is 1, for example, only gas phase is there, and component is also 1 plus 2, so F is equals to 3 minus 1. So basically, if you are working in one phase, you have to fix two properties. So we have fixed what? Pressure and volume we have fixed. Okay, but this changes when, the phases change. For example, you are working with a mixture of uh, water and air, or water or steam, sorry. Okay, so it changes. Clear? Now, next is reversible. So processes are of two type: reversible and irreversible. I hope, okay, that was not the part that I was going to take anyway, Abhishek. Okay, but in detail, I have told you. Look, Gibbs phase rule. If you, I'll just spend 2 minutes over it, not much, because I need to focus on some topics. Okay, I really will not be able to cover everything. Okay, so let me add some slide. Now, Gibbs phase rule. Gibbs phase rule is basically tells you the degree of freedom, or the number of independent intensive properties required to fix the state of system. What is the formula of Gibbs phase rule? P plus F is equals to C plus 2. P is what? Phase. This is degree of freedom, or the properties, components, and 2 is a constant. Now, for example, you are working with water. So what is water? What is phase? Tell me how many phases are there? Phase. Quickly tell me. One phase. Component. How many phases? How many components? No, 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 no. Component is just one, H2O. I'm not talking about molecules here. I'm not talking about elements here. Okay. Component is H2O. All over you see, if you have this. So here is also H2O. Here is also H2O. Here is also H2O. Nowhere you will get OHO2. Okay. Component is the compound. So compound is what? H2O is the compound. Okay. So is it clear? Everywhere you have H2O, nowhere you have HO2, because HO2 is a different compound. Okay. Now, so component is also one. So that is what you can say: phase is one, F, component one, plus 2, F is equals to 3 minus 1, F is so for water, if it is in just liquid state, if it is in just liquid state, then you can define by just two properties. But what happens if it is water and steam? Then yeah, it will be very thin. You see, this is then okay. If you want, I can do this as well. I have no problem. So now, if water and steam, then we have three. Then number of phases, P plus F is equals to C plus 2. Is it okay, this thickness? I think it's very thin. If we have water and steam, water plus steam. So tell me number of phases. Number of phases, 2. Number of components. Components. Component is 1. Component is 1. Because in water also, it is H2O. Steam also, it's H2O. 1 plus 2. So F is equals to 3 minus 2. F is equals to 1. So only one independent intensity property is required. Okay. So that is how you can find out, although it's not very, like usually don't get question directly. But anyway, now you know. Let's move ahead. Let's move ahead. So we were going to discuss irreversible and reversible. I hope you already have heard this word so many times. Let me drink a sip of water and then we'll continue. I think we have come what? How many slides we have covered? Not much. Have you heard about reversible and irreversible processes? Or reversible in general and irreversible, okay? Okay. So reversible process is a process. If you see, like for example, you are here. You have a hill, that is your hill, and you are going from here to here. So of course, like you have spent some energy, some metabolic energy, and some something is lost, energy is gone. But tell me one thing, if you are coming back from here to here, will you get this energy back? No, of course. When you are coming down also, you are going to release some more energy, right? So that means basically continuously when you are going up, you have given some energy to the surrounding. When you are coming down, you are giving some energy to the surrounding. Okay, let me explain it one more time. So let me increase the thickness. It's not fun actually. I mean, it's very thin. Okay, look, this is your hill. Okay, you are here. Now, when you are going up, you have spent some energy. Now, I know when you will come down, you will not absorb this energy. But just assume that when you are coming down, when you are coming down, you are absorbing back this energy. Just assume for 1 second. Now you see you have done a process. You have moved from 1 to 2 and then come back. Okay. So basically you move from 1 to 2, then reversed and come back. So in this case, when once you come back, whatever energy you have spent, you have given to the surrounding, you have absorbed back. So tell me, what is the net effect on surrounding in this process? Zero. Very nice. Because when you are going from 1 to 2, whatever energy you have spent, whatever energy you have given to surrounding, when you came back, when you reversed back to 1, you have absorbed. So basically, you did not give anything. In this whole process from 1 to 2, then 2 to 1, net effect on surrounding is zero. So if any process can happen in such a way, it is called as reversible process. Okay, if any process, although it is not possible, it cannot happen, but if it can happen, it is called as a reversible process. So basically, if a system is called as reversible, if the both the system, because you see, system is not net effect on system also is zero, because system has spent some energy, then it is absorbed back. So system has not lost anything eventually. Okay. So net effect on both the system and surrounding returns to its initial state by reversing the direction without leaving any effect on system or surrounding. So if you can reverse a process in such a way that it will not affect the system and surrounding it any way, then it is called as reversible process. It is shown by continuous line. Okay, it is shown by PV. So I will show it. Okay, I will show it like this: 1 2 2, and I will go like this. I will go like the continuous line. I will show. Okay, the system as well as surrounding can be completely stored. What about irreversible? So the actual case, you see, when you are coming down, you are also, losing heat to surrounding. That means net effect on system, or so when you are coming back, the system did not restore to its original thing. Okay, so basically you have disturbed the system or surrounding, and when you are leaving some effect on system or surrounding, it is called as irreversible process. So a process is said to be irreversible if the system does not return to its initial state due to impact left on the surrounding, and the system and surrounding cannot be nor surrounding. A system nor surrounding can be completely restored to its initial condition. Okay, it happens, and that is the reason it can only happen in one direction. Okay, it is represented by dotted line. You can only show it by dotted line. Yes, someone has raised hand or something, I think. Who is this? So it is shown by this. Amit, in reversible process, we can say that there is no loss of energy of system and surrounding as well. That is the reason. No, like both the system and surrounding is restored. Whatever surrounding absorbed, it gave back. Whatever system absorbed, it gave back. Okay. Who raised some hand? Someone was who was that? Okay. Any question? Anyone else? Okay, I don't want to raise hand. Why I raised hand? Okay, what are the forms in which system can lose the energy? System can lose energy in any form. It can lose, basically, look, there is one way system loses energy, and that is heat. That is the most common way of losing energy. In fact, most of the systems, in fact, heat is the byproduct of anything. Okay, so most of the energy is always lost in terms of heat, and if you are not using any energy. But you see, look, pressure, look, you have to understand one thing, Ravi Teja. What is pressure? Pressure is basically the average momentum of atoms or molecules. Okay. So if I am, like system is at high temperature, high pressure, that means reversible system is possible in, no, it's not possible. No, it's not possible. There is no reversible system. Yeah, Ravi Teja. So basically, pressure loss, you cannot lose pressure basically. Like, pressure will be lost in other terms. For example, energy will be going out. So if energy is going out, the temperature of the system will reduce, or and in you see, its density may change, and then pressure loss will happen. Okay, pressure is not crossing the boundary. Okay, what is crossing the boundary? Energy is crossing the boundary. Okay, so if energy is crossing the boundary, it is the after effect that the pressure is decreasing or increasing. Okay, so pressure loss, we in general terms we say pressure loss, but it is not the pressure that is losing. Yagna, no, there are no real reversible systems, reversible process or reversible systems. Okay, chalo, let's move ahead. Now thermodynamic cycle. Thermodynamic. So what is a cycle? You tell me. What is cycle? Cycle is basically you start from somewhere. Bhavyashri asking for reversible and irreversible processes. Look, they are reversible process example. There are no reversible processes. Irreversible process example. All the processes around you are irreversible. For example, you have moved your hand, it is an irreversible process. You have walked from your room to your kitchen, it is an irreversible process. Okay, all the processes are irreversible. Whatever you do, whatever happens around you is an irreversible process. Okay, yes, yes, Abhishek, that is correct. We are losing energy only. Okay, but pressure is basically, it is happening in terms of pressure. Pressure is the after effect, is happening inside the system. Okay, now is it clear, Bhaveshri? So thermodynamic cycle is what? It basically repeats its state. It basically comes to its original state. Okay, you start from here, you go here, you go here, then you go here, then you go here, then you go here, then you go here. But as soon as you reach back, you have completed the cycle. So for a cycle, pressure is not work energy. Work, you can utilize, you can do work using pressure. Okay, look, don't please do not mix the words. You have to understand that if the pressure is high, you can utilize more work out of it. Okay, so pressure is not an energy. You first of all, you have to understand pressure is not an energy. Okay, pressure is a property, work is an energy. Okay, so I'll tell you one thing. It's a very funny thing. Teaching, like teaching, if you when you teach, students, you have to be very cautious, because if you tell them so many things, then they will get confused. You see, if I'll just tell you very few things, then you will be very happy ki, okay, I understood everything. But when you explain so many things, no, so because you have a very raw mind, so you cannot differentiate between pressure and energy. You are confused, you are mixing pressure and energy. I told you pressure is a property, work is an energy. Okay, they are completely, I mean, they are different, they are not same. So you cannot say pressure is like a work energy. So what I'm trying to tell you is, do not try to mix everything up. Just chill, study, and then try to revise things. And thermodynamics is a subject that you will never understand the very first time. Whoever is studying the very first time, you will be very confused after learning it. It minimum 3 revisions are required to understand thermodynamics, minimum. Okay, you will slowly start getting things, do not worry about it. Okay, chalo, let's move ahead. So basically, if you are coming back to the original state, so cycle means initial state is equals to final state. Okay, so minimum number of processes are minimum two required. Okay, one you will go and then come back to minimum to two. Then it can be three, it can be four. Four, how four will look like? You will start from here, you will go like this, you will go like this, you will go like this, and then four. Five, it can be anything. It can be any number of processes. So, but the minimum is two. But the minimum is two. And for the cycle, difference of all the properties is zero. We will understand this in some time, but just note it down for, I mean, just understand this. For a cycle, change, for a cycle, change in property will be equal to zero. Just, I'm not explaining this. I will explain this in some time. Okay, not now, but just keep this in your mind that what I am saying. Okay, chalo, let's move ahead. Now, point and path function. Point and path function. So, what is point and path function? So, as the name is suggesting, first of all, let's understand path function. Okay, my cursor is creating some disturbance. What type of disturbance? Okay, yeah, that is my pen that is doing some disturbance. Okay, I mean there's a button here. If I click, it just does something. So let's understand path. So what the path function means? Path, basically a function that depends on path. Simple words. Okay, if we have a function that depends on path is called as path function. What does this mean? It actually means, for example, you see, look, I have a PV diagram. I am going from 1 to 2 by using a path A. Okay. Now I am going with this path, path B, or I am going with this path C. So tell me if I have a property that is a path function. Okay. If I have a property that is a path function, so will it be same? Let's say a property X. So will this property or change in this property for path A, will it be same for path B, path C? Is it correct or not? You tell me this. Do you think? No, of course not. Because you see, this is, let us say, this is X1 and this is X2. Okay. So if I am going from path A, then my change, and it is going to depend on path. So my Okay, yeah, sorry. So my change in x from path A will not be equal to x2 minus x1. Simply. Okay. Okay. So basically, you see, I can tell you in this way. You see, when I am taking this path, A path, so this area it is covered is this, right? When I am taking B path, the area that is covered by this path is the red one. When I am taking this C path, so area covered is this one. Okay, so the area covered with each path is different. Okay, and if a property is going to be a path function, then if you change the path, that property will change. So you cannot simply just write x2 minus x1. Okay, so basically a path function depends on the path followed by the process. Its value dependent on the path followed. So its value is going to depend by what is my x2, what is my x1, what is the final change. It is going to be dependent. So it is, they are not equal. They depends on the path. So delta XA will not be equal to delta XB will not be equal to delta XC. Okay. For example, heat and work are path function. Again, we will discuss this, but don't worry about it now. Okay. Just know that heat and work are path function. Okay. Now, I would say a point function. Now, point function, what is a point function? It is independent of path. So it does not depend on path. Now, whatever path I am taking, as long as my first state and second state is fixed. So whatever path I am taking A, B, C, or any path. But I am starting from here, I am reaching here. As long as my initial and final state is same, the value of, let me say, point function as y. Okay, so y is a point function. So change in y for path A will be equal to change in path y in path B. It, whatever path you are taking C path, you are taking D path, You are taking E path, whatever path you are taking, as long as my 1 and 2 is same, change in the point function will remain same. It does not matter. And a point function is called a property of a system. A point function is a property. A path function, it is not a property. You have to understand this very clearly. It is not a property. So heat and work, they are not a property of the system. Okay? Heat and work, pressure, temperature, volume, enthalpy, internal energy, entropy, they are all properties of the system. Okay? So now I can tell you this thing. Now I can tell you this statement that change in property. So again, look, I started from here. So my property, let us say, was P2. Okay. Then for a cycle, change in property for a cycle. So change in property for a cycle is equals to whatever. So what is change in property? Final position minus initial position. Now my final position is what? P2 at this point, and initial position is what? Also 2. So also it is 2 for a cycle. I am saying, because cycle I started from here and I reached back. Okay. So it will be equal to 0. It does not matter. I go, I take this part, I take this part. As long as I am coming back here, change in property will remain 0. Because it is, property is what? Property depends on only the state, only the point where you started or where you ended. Okay. So whatever path you are taking does not matter. Okay. So that is your point and path function. Now these things is very important. Work and heat transfer are path function. They are not properties. Basically, path function, they are not properties. Just simply know this. Okay. Now exact and inexact differential. Exact, and so it is also similar to path and point function. You see, point functions are exact differential. What do you mean by point functions are exact differential? So exact differential means cyclic integral of the point function will be equal to 0. Cyclic integral. Okay. So you see, I started from 1, went to 2, and then came back at 1. Okay. So change of property at, now what is cyclic? Let me write it here. So the cyclic integral of a variable is equal to 0 exact differential के लिए. That means cyclic integral of a property will be equal to 0 of a change in property. Okay. So what is cyclic? The cycle, it is starting from, so when I say this, so I write delta PA plus delta PB is equals to 0. Cycle means what? This plus this. Oh, sorry, this plus this. Yes. Now it is equals to 0 for exact differential. So I can write delta PA is equals to minus delta PB. Okay. Now what is this? Change in property by a path. So I can write P2 minus P1. What is this B? So B is final minus initial. So it will be minus P1 minus P2. So if you reciprocate this, it is P2 and P2 minus P1. It's simply telling you that does not matter if you are taking path A or path B, you can simply write P2 minus P1. Simply you can write it the same. Okay, that's why you see, look, that's how you do. Like, for example, if you want to calculate change in enthalpy for path A, so what will you do? H2 minus H1. You have to calculate change in pressure for path A. What will you do? P2 minus P1. Simply. Okay. So you can write it in this way. But in exact differential, the cyclic integral is not equal to zero. Yani ki this delta P, it is not equal to zero. That means these things, they are not equal to, they are not equal. Okay, they are not equal. That is the reason that you can never calculate change in work for path A. Have you seen this equation anywhere? Tell me. Work 2 minus work 1. Or change in heat A is equals to Q2 minus Q1. Have you seen this equation anywhere? Yes or no? Yes. You cannot see this because these are path function. You cannot calculate simply by this. You have to integrate. For example, you are taking this path, you will take little area and then you integrate it for the whole area and you will get this. Then you can calculate, so it will be basically equal to area. Okay, we will see this when we come to work. And this is also area. Okay, but what I want to tell you is path function cannot be calculated like this. It is not correct. It is not correct. But point function you can directly calculate like this. Delta volume, change in volume in the process A, V2 minus V1. Change in entropy is equals to S2 minus S1. For all the properties you can do that. This. But for work or heat you cannot do this because they are path function. Okay. Is it clear? Yes or no? Okay. Chalo. Let's move ahead then. Thermodynamic equilibrium. Thermodynamic equilibrium. Okay. Now, anyone, any idea about what is thermodynamic equilibrium? A lot of people confuse thermodynamic equilibrium with thermal equilibrium. In the interview, they will ask you what is thermodynamic equilibrium. You will start telling thermal equilibrium. They are not equal. They are not equal. Pranjul, look, it will be really a tough, like I have to explain so many things. What you can do is there is recording. You please just check it once. You just try to understand, grasp, absorb it slowly. If you have any doubt, we will have next class. You can ask the doubt. Because if I again, please, it's a humble request. If I start explaining everything again, no, then it will be little difficult to cover everything. Okay, please. So you see the recordings. It will be available tomorrow. I think maybe tonight. Just see it, absorb it. If you don't understand, ask in the next class. Okay, but come up with a specific doubt. If you just say, sir, please explain again, then it will be really difficult. Okay. So just ask some specific doubt. Sir, okay, how are you doing this? How are you doing that? I will be more than happy to answer. Okay. So, thermodynamic equilibrium. Basically, a system is said to be in thermodynamic equilibrium when it satisfies three conditions. What are the three conditions? Mechanical equilibrium, thermal chemical equilibrium, and thermal equilibrium. Okay, these three conditions must be satisfied. Now, what do we mean by mechanical equilibrium? Mechanical equilibrium simply means that there should be no imbalance force within the system and between the system and surrounding. There should not be, so basically, if this is your system, here pressure is equals to, what is the pressure outside surrounding? 1 atmosphere. So this should also be at 1 atmosphere, because for example, if it is at 2 atmosphere, so there is an imbalance force between system and surrounding. You see, inside pressure is higher, outside is, Shivam, 1 second. Let me complete this, then I'll read what you have written, something long. Okay. So, what I'm trying to tell you is that if the pressure is not same between system and surrounding, then there will be some imbalance at the boundary. So, you cannot say that it is in mechanical equilibrium. So, basically, you can say mechanical equilibrium is equality of pressure. Equality of pressure. Okay. What is chemical equilibrium? Chemical equilibrium is basically no chemical, sorry, no chemical reaction inside the system. Okay. So if there is no chemical reaction, so there will be no change in chemical composition of the system. Okay. So that we were in, like in that Gibbs phase rule, if you take H2O, so yeah, composition means it has hydrogen and oxygen, but component is one only. Okay, so you have to, yes, rate of back. Basically, there is no reaction that is happening. Okay, so you cannot say that rate of forward reaction or rate of backward reaction. It can actually, still, if you say rate of forward and backward means component is changing. Okay, but there is no chemical reaction. In simple words, there is no in thermodynamics we basically neglect any chemical reaction in our system. Okay, so basically here the criteria is equality of chemical potential. Chemical potential. Now thermal equilibrium is same. It is basically equality of temperature. So between system and surrounding there will be no inequality of temperature. So if these three conditions are satisfied, so you see thermodynamic equilibrium is not equal to thermal equilibrium. It is a part of thermal equilibrium is a part of thermodynamic equilibrium. Okay. So if all three conditions are satisfied, then only you can say that thermodynamic equilibrium, your system is in thermodynamic equilibrium. Okay. Now Shivam was saying something. If thermodynamic process returns to its original position, then we can say that the cyclic integration of work done is zero. No, you cannot say that. How can you say that? You see, let me go back. Let me add a page. So you see this PV. Once you go from here to here, okay, 1 to 2, you have done some work. Okay, you go. So it will be work in the process A. So basically, while going from 1 to 2. Now, when you go from 2 to 1, of course, you will not go back, because if you are going back in the same process, it is a reversible process. Reversible process is not possible. Okay. So you cannot take this process. You will have to take some other process. So you will take what? You will take this process. Okay. Now it will be V. Now W, B it will take. So cycle is completed. Yes, it is returned to its original state. But WA is not equal to WB. Why? What is WA? WA is this, the area under the curve. What is WB? WB is this area under the whole curve, this one. And they are not equal. So if they are not equal, you cannot say cyclic integral of work is equal to zero. It is not. How it is zero? If it is equals to zero, that means then I have to write WA plus WB is equals to 0 and WA is equals to minus WB. But this condition is not satisfied. No, I am saying it is not same. Okay. Yes, following same path means reversible process. Shivam is saying for work 0, we need to follow same path. Yes, same path you have to follow. Now, Shivam, 1 second. For here, so many doubts here. But sir, work done by system is equal to heat absorbed. That is for a cycle, yes. But Again, heat transfer, we are not accumulating for heat transfer. Heat transfer will be something else. Okay. So heat transfer here, work transfer is happening. WA plus WB is equals to QA plus QB. Neither this is same nor this is same. Okay. So cyclic integral of work is zero is a completely different story, and this is completely different story. Okay. Yes, net work done. Okay, net work done will be zero for reversible process. No, no, no. I am not talking about dissipation effect. That is completely different. Okay. So, ठीक है. Let's move ahead. Thermodynamic equilibrium is done. Ideal gas equation. Quickly, let us. What is the time? Okay, not much time left. We still have to cover a few things. Let's quickly let me move ahead. Okay. So ideal gas law, there is nothing much to, I think you have already learned this in 11th and 12th. Okay. So basically ideal gas law is defined by using three laws: Boyle's law, Charles law, Avogadro law. Okay. Boyle's law says that at constant temperature and number of moles, okay, number of moles, if we have constant temperature and number of moles, volume is inversely proportional to pressure. Volume is in, it is experimentally defined. Okay, it is experimentally defined. They kept temperature constant and number of moles constant, and what they saw, that when volume is decreasing, your pressure is increasing, and when volume is increasing, your pressure is decreasing. That means they are inversely proportional. Okay. Then again, experimentally Charles defined that if you take pressure and number of moles as constant, then volume and temperature are directly proportional. So if volume is increasing, temperature increases. If pressure is constant, again mark my words, if pressure is constant, then this will happen. Okay. And if volume is decreasing, temperature is decreasing. Avogadro law was experimentally again defined: at constant pressure and temperature, volume is directly proportional to number of moles. So we have just combined volume, volume, volume. We have combined this, and we have got PV is equals to nRT. P is our pressure, absolute pressure. Okay. V is the volume, N is number of moles, T is absolute temperature, and R is universal gas constant, and its values, it always remains same, 8.314 joule per mole Kelvin. Now this is the equation that mostly chemical engineers use. Chemical engineers. Why? Because it has number of moles. N is number of moles. So they mostly use this equation. We do not use this, okay, as a mechanical and aerospace. I mean, we use this, but not very frequently. What do we use? We use in terms of mass. So what is happened? By N is number of moles. Number of moles is what? Mass upon molecular weight. Okay. So let me substitute N here, and I will get this. Okay. Now let me take N as outside and capital R plus molecular weight, and this is called as R, which is characteristic gas constant. Characteristic gas constant. So again, remember these words: number of moles is equals to mass upon molecular weight, and specific gas constant is equals to universal gas constant upon molecular weight. Now this is characteristic gas constant. It will be different for each gas. For air it will be different, for carbon dioxide it will be different, for each gas it will be different. So for water you can write it like this: R is equals to, because what is the molecular weight for water? 18, H2O. Okay, molecular weight is what? 16 plus 2, 18. And for air, actually it is water vapor. Okay, it is steam. We are only talking about gas. For air, it is molecular weight is 29. So you can calculate. These are very common. Otherwise, they will be given to you. You can calculate for nitrogen as well. Okay. So if you know the molecular weight, you can calculate characteristic gas constant. So we use basically this equation. Mechanical engineers and aerospace engineers mostly use this equation. Although you use that as well, but most frequently you use this. Okay. So this is your ideal gas equation. Now it is basically equation of state of a hypothetical ideal gas. It gives you good approximation of real gas. Basically, we all know that there is no ideal gas. But when real gas is at low pressure and high temperature, mark it is an objective question. When real gas is at low pressure and high temperature, then then it approximates as ideal gas. Real gas has low pressure and high temperature behaves as ideal gas, and you can apply PV is equals to MRT at this condition. Now, what happens if it is not showing, if it is at high pressure, for example, and low temperature? That means you cannot apply ideal gas equation. You cannot apply. Then what will you do? There is a variable. Actually, there are different equations of state like van der Waals equations and all. But a simple version is you account for a compressibility factor. It accounts for a compressibility factor. So for you see, PV is equals to MRT. Now P mass per unit volume into RT. P is equals to specific volume upon RT. Okay. Oh, I'm sorry. The one this it will be volume upon 1 second. Sorry, it is density. This is density. Let me not write it like this. Let me write volume per unit mass is equals to RT, specific volume upon RT. So specific volume upon RT is constant. Okay. Now, in order to ideal gas to satisfy this constant must be zero. But for real gases, it is not equal to zero. This constant is called as compressibility factor Z. Okay, it is called as Z. So Z is ideal gas. For ideal gas, it is equals to 1. For real gas, it is not equals to 1. It deviates from 1. What is 0? Why 0? Did I say 0 somewhere? Z is equals to 1, I said. I don't know what 0 you are saying. Is it clear? This much is clear. Tell me yes or no quickly. Okay. So let us come to the last topic of today, which is Zeroth law. Okay. So Zeroth law is simple law. It basically tells you, it states that if a body A is in thermal equilibrium with body B and body B is in thermal equilibrium with body C separately. So let us take a body. Let me call it as B. Okay. Now let me take a body A. Now what I am saying is, if this body A is in thermal equilibrium with body B, simple. When will be in thermal equilibrium with B? When its temperature and its temperature will remain same. Okay. Okay. I don't know this temperature. I don't know this temperature. Okay. Let me say T. But these A and B will be in thermal equilibrium when their temperature will be same. That means if TA is equals to TB, now let me take one other body, C. And I am saying TC. This is TA, let us say. Okay. And I am saying this C is also in thermal equilibrium with body B. Okay. When will this happen? When this both, it will happen. Look, again, let me rephrase this again. I have a body B and let me bring a body A in contact with this body B, and its temperature is not going to change. So what does it indicate? Okay, if you are bringing two bodies together and their temperature is not changing. What it simply means that their temperature is same. Okay, so that means Ta is equals to Tb. Now I am taking that body B somewhere else and I am joining it with body C, and still their temperature is not changing. That means Tc is equals to Tb. Okay, and if this kind of scenario is there, that means A and C are also in thermal equilibrium. A and C are also in thermal equilibrium. Okay, did you understand this? But I have a body, I have one body, and now I am bringing a body in contact with this, and their temperature is not changing. That means their temperature is same. Okay, now I keep my first body as it is. Now I bring a third body and bringing back to the first body. They are in contact, and their temperature is also not changing. That means they are also in thermal contact. That means both body A and C are in thermal contact, thermal equilibrium. Okay, so it states that if body A is in thermal equilibrium with body B, and body B is in thermal equilibrium with body C separately, then body A and C will be in thermal equilibrium with each other. Okay, so this is the conclusion. So basically here we take a reference body. So this is our reference body, which is used to determine the temperature, and this reference body is called as thermometer. Okay, and there will be one property that will be changing when I bring these two bodies in contact. If the temperature is changing, if the temperature is changing, that means it is it will be indicated through a certain property, and that property on which the property of these bodies on which temperature is dependent is called as thermometric property. Okay, so again, I could, like I could spend a lot of time in this explaining, but I am intentionally not. I usually, like spend a lot of time. I actually take a 2 hour lecture on Zeroth law of thermodynamics, but I am not, because I think it is not very important for you. But I mean, I know it could be there, so I am covering all the basics that is required. Okay, so basically, you have a thermometer and you have a thermometric property to measure the temperature. These are two main things. Okay, so there are various types of thermometers. First is, I am not covering the working of these, just the important points. So we have resistance type thermometer. It works on wheat stone bridge, and the thermometric property is resistance. So basically, if the resistance is changing, its temperature is going to change. You see, if the temperature is changing, if the resistance is changing, you see, uh, that is called as wheat stone bridge, right? This is something like this galvanometer and all, and we connect it with the supply, and we supply power. We take resistances constant in all of them. Only one resistance I'll let change. So based upon the current that it is showing, the resistance is going to change, and this resistance, the change in resistance will tell you the change in temperature. So basically, resistance is dependent on temperature. Well, temperature is dependent on resistance. That's why resistance is called as thermometric property. Okay, now the next one is thermocouple. Thermocouple also you may have heard. Okay, and the principle is Seebeck effect. Seebeck effect. Okay, and its thermometric property is potential difference or voltage difference. Mercury thermometer, so you all have seen, right? The normal thermometer that we use, you put it in your mouth or somewhere, and the mercury expands. Mercury expands. So its volume changes, yes or no? Or you see the length scale on the, if this is your mercury thermometer, then the volume of mercury rises up. So basically there are scales here, right? So based upon scale you can read the temperature. Okay, so based upon the change in volume or change in length, you can read the temperature. Okay, now there is constant volume thermometer. Here thermometric property is pressure, and constant pressure thermometer, here the property is volume. Okay, very quickly, let us see, a little bit of, we will wrap up it at 11. Okay. Now, like there was no method of measuring the temperature. When Zeroth law came, there was no method of measuring the temperature. Like we had no thermometer. Okay. So we basically defined some methods to measure the temperature. Thermometer came much after that. Okay. So we defined separate methods of, to measure the temperature. And the measurement process is quite random, like there is no basis for it. Okay, you say 0 degree Celsius, but how do you measure 0 degree Celsius? Okay, there is no point in saying that okay, ice is, like you say ice melts at 0 degree Celsius, or it freezes at 0 degree Celsius. But what is 0 degree Celsius? It has no physical significance of it. You can say it is 100 degree Celsius as well. Nobody is going, or I, you are saying it is 0 degree Celsius, I can say it is 50 degree X, whatever it is. It's up to me how I want to define this. It's very arbitrary. Celsius is a person who has said that when the ice freezes, I will say zero. When the water boils, I will say 100, boiling point. It is my choice. I can say 250 as well here. I can just convert it in some way. Okay, so temperature scales are arbitrary, as you chose, as you wanted, as the, as these people who were working on these experiments, as they wanted, they defined it. There was no, quick, or say strict restriction on that. Okay, so in order to able to assign a number to the temperature of a body, it is necessary to agree upon a method for setting up the temperature scales. So we need to choose a thermometric property. So we can choose any property. We can choose a length or the resistance or the pressure, and we will call this property as X. We will call this property as X during the calculation of the temperature. Okay. So the first method that we used was before 1954, and it was based on two reference points, ice point and steam point. Okay, and we took a linear temperature. We look, what is X? Thermometric property. And I have just told you that the temperature depends on this property. Now how does it depend? We took a linear relationship. Okay, now I have fixed 2 points. I have I had water, and I fixed ice point as 0 degree Celsius and steam point at 100 degrees. It was my choice. If I was someone else, I can take it as anything. But Celsius chose 0 degree Celsius and 100 degree Celsius. And at this point, the property is X. I means ice, and here property is XS, which is steam. Okay, so what is this? This is thermometric property at ice point. Whatever the value is, it does not matter. But at that point, thermometric property at steam point. Okay, now what do we have? We have a linear relationship. So what will we do? By we have T is equals to AX plus B. So let us take ice point. Let us take ice point. So temperature is what? 0, A, xi plus b. So we can calculate b from here. B is equals to minus axi. Okay. Then let me take steam point. 100 is equals to axi plus b. Okay. So from here I can say 100 is equals to AXS, sorry, AXS, minus, I can put the value of B here, minus AXI. So it is AXS minus XI. So what is A? A is equals to 100 upon property at steam and ice point. So now I have gotten A and B. I can substitute in my main equation. So T is equals to 100 upon x minus xi x plus minus actually minus a x I. Okay. And what is A? A is again same. What is A? A is 100 xs minus xi into xi. Okay. So I can take 100 xx minus xi x minus xi. So I can eventually write this as t upon 100 is equals to x minus xi upon xx minus xi. Okay, so this is my general equation. This is my general equation. So what can I do? You see, these values are known already. It will be given to you. Now they will say calculate temperature when x is equals to 5. So you know this, you know this, you know this. You put 5 here and you can calculate temperature in degree Celsius. In degree Celsius. This is degree Celsius scale. Okay. So here temperature is basically, what is this? Temperature is a function of the thermometric property. Okay. So that is how we have defined this. You see, now Fahrenheit, basically we can convert this. We can convert this into several forms. For example, what do we have? T minus Ti upon Ts. You see, this is what is this form? Can I say it is T minus Ti upon 100? 100 is what? Ts minus Ti is equals to x minus xi upon xx minus xi. Can I say this? Because you see, if I put 0 and Ts is what? 100 minus 0, so I will get the same result, yes or no? Quickly tell me, yes or no? Same result we are getting, no? Okay. So we can use this. So we have Ts minus Ti is equals to x minus xi upon xx minus xi. Okay. So in degree Celsius, I have T minus 0 upon 100 minus 0 is equals to x minus xi upon xx minus xi. What about in degree Kelvin, let us say? Fahrenheit, so I have written it here. What is in Kelvin? What is ice point in Kelvin? Ice point in Kelvin. Yes, 273. And what is steam point? 373 minus 273 is equals to x minus xi upon xx minus xy. Similarly, you can calculate for Fahrenheit as well. Okay. So this is the conversion of one scale to another scale. So for example, you want to convert you Fahrenheit uh, degree Celsius to Fahrenheit. You can use this relation and convert it. Okay. So this is how you can use this. Last is after. So this was before 1954. After 1954, basically we had several problems with क्या नाम है, the previous method, because you had to first of all calculate two temperatures, ice point and steam point. Now anyway it was very difficult to calculate, to measure the temperature. It was very difficult at that point of time, and now you are measuring two temperatures, so basically the margin of error was higher. So what did they do? They bring it back to one single point, and that point is called as triple point. Okay. So here we use ideal gas equation. Now this is based on a single point, based on single temperature reference. Okay, so we took ideal gas equation, and P is equals to mR by T. Temperature is directly proportional to pressure, and we have taken a proportionality constant K. Okay, now we have defined temperature. Triple point temperature is of water is 273 and pressure is 0.611. Okay, now what will I do? I have this relationship T is equals to Kp. Now I can put TTP is equals to K pressure at triple point. So K is equals to TTP upon PTP. Now I can substitute the value of K here, and temperature is equals to TTP upon PTP into P. And what is this? 273.16 pressure upon, you can put the value of this as well, but usually it is written like this. Okay, so temperature is equals to 273.16 P upon PTP. So if you at a given pressure, if they say calculate pressure, calculate temperature at the pressure of 100 kilopascal, so you put this here, calculate temperature. So this is how they started measuring this. Okay, so there were, can have a different, all the resistance thermometer and all that you can define based upon this equation as well. Okay, so I hope this is it for today. I know that we have covered a lot, but because it is a 2 hour class, so we will be covering a lot anyway in each and every class. How you can benefit with this is you have to revise, because okay, today's session was completely isolated. Most of the things we are not going to use later on, but there are so many concepts that we covered. But from next sessions we will be covering so many concepts like work transfer, first law, heat transfer, processes, different processes, constant volume, constant pressure, and all that, and we will be using them each and every day. So revision is very important. If you are not revising, you're not utilizing the what I am trying to give you. Okay, so please revise. I have tried to cover most of the important things that is required from exam point of view, for any competition point of view, I would say. Okay, so please revise, and we will meet in the next class. I don't know when we will meet, but it will, I think it will be communicated to you. Okay, so let's stop here already. It's 11. Yes.